Okay, so I ended the last video on talking about turning points, and I kind of rushed through it, so I want to emphasize that if you have a polynomial with a degree of a certain number, the graph has at most one less than that number of turning points. So here, this polynomial had a degree of 5, and it had 1, 2, 3, 4 turning points. So in general, if f has a polynomial of degree n, then the graph of f has at most n minus 1 turning points. Okay, let's talk about how to graph polynomial functions. We spent the last section graphing quadratic functions. Now we're going to talk about polynomial functions. This is anything basically where the degree is 3 or more for your polynomial. Okay, first of all, you want to use the leading coefficient test to determine the graph's end behavior. Does it rise? Does it fall? Left? Right? Right? And so on. So the end behavior. So you can look at that little chart that we had there. We're going to look at find the x-intercept by setting the function equal to 0. And if there's an x-intercept, we talk about the multiplicity. And so once you find the x-intercept, you look at the multiplicity because that tells you what happens at each x-intercept, whether it touches the graph and turns around, whether it crosses, and so on. Then you want to find the y-intercept by putting in 0 for x. And then you want to look and see if you have symmetry, because symmetry will help you draw the graph. And to find symmetry, remember that last chapter, you plug in the negative x, and the function stays the same, and you have y-axis symmetry. If you plug in the negative x and it changes every term, then you have origin symmetry. And generally, we're going to see this. If we see any of this, we're going to see this right here. We're going to see the y-axis symmetry. We don't hardly ever see the origin symmetry. And then we use the fact that the maximum number of turning points of the graph is n minus 1, where it's the degree of the function, just to make sure that your graph is drawn correctly. Okay, so look at example 9. We're going to graph this polynomial function. We're going to go follow all those steps. And if I were you, and I'll give you a copy of this on the exam. So I'll give you a copy of this and then the copy of the end behavior leading coefficient test. So we're going to follow these 7 steps. I want you to go ahead and label these 7 steps. Do work. The first step is to use the leading coefficient test to determine the end behaviors. So we use the leading coefficient test. For end behavior. And you don't have to write that every time, but step 1 is what we're doing. So we're going to look at this and we see that it has a even power. So n is even. And the leading coefficient is positive. You have a positive 1 there. So we go back to our chart here. N is even, and the leading coefficient is positive. So n is even, leading coefficient positive, or this case right here. So we have rise left, rise right. So I know that when I draw my graph, it better be rising left and rising right. So I know rises left, rises right. And I don't know what's going on in the middle, but I know that's going on. Second thing you want to do is we want to find the x-intercept. Okay, so x-intercept. We plug in 0 for the y, so 0 equals x4 minus 2x squared plus 1. 0 equals, I'm going to factor this. And when you look at this here, notice how I have 3 terms. There's no GCF. So x squared goes in here and here, but doesn't go in here. There's no number that goes in all 3 of them. So I'm going to try this AC method. 1 times 1 is 1, and the b is negative 2. What 2 numbers multiply to give me negative 1, but add up to negative 2? These 2 multiply to give me 1, and add to give me negative 2. So I get x to the 4th minus 1x squared minus 1x squared plus 1. And now my group, I get x squared minus 1, minus 1, x squared minus 1. I get x squared minus 1, x squared minus 1, which gives me x plus 1, x minus 1, x plus 1, x minus 1. So I get x equals negative 1, x equals 1, but notice how it has a multiplicity of 2. It has a multiplicity of 2, it has a multiplicity of 2 because this one occurs twice. I get x equals 1, x equals 1, x equals negative 1, x equals negative 1. So look at this, I have negative 1, 0, and 1, 0, and we know that because it has even multiplicity, the graph is going to touch each 0. I'll say each 0, but in this case, negative 1, 0, and 1, 0, and turns around. Okay. Now we're going to find the y-intercept. I'm going to run out of room here, so I hope I'm a little bit smaller here. I'm going to find the y-intercept. So I'm going to plug in 0 for x, so it becomes f times 0, or f of 0 equals 0 to the 4th minus 2 times 0 squared plus 1. 0 minus 0 plus 1, which is 1. I get 0, 1. Okay. And do we have any symmetry? So I'm going to plug in the negative x for the function. Well, let's go ahead and write our original function down. Original function with f of x equals x to the 4th minus 2x squared plus 1. When I put in the negative x, what happens? I get x to the 4th plus 2x plus 1. And, oh, I made a mistake here. Good. Erase this and start over. So I plug in the negative x, I get negative x to the 4th minus 2 negative x squared. I forgot the square there. Okay. So this actually becomes x to the 4th, it becomes x squared. So I get x to the 4th minus 2x squared plus 1. Notice how these are the same. That means we have y-axis symmetry. It's even function, which means y-axis symmetry. Okay, and then we'll look at max turning points. Okay, so we have degree is, go back to our function, the degree is 4, we do 4 minus 1, which is equal to 3. So you should have 3 turning points. Okay. So I have some room here. I'm going to go ahead and erase this so I have some room. I'll recopy this. Same y-axis symmetry. Okay. I need some room here. And I'm going to go ahead and draw a graph here. Now I'm testing like using graph paper. Go ahead and draw the tick marks here, tick marks here. Okay. And the first thing we know is that we're going to rise right, rise left, or rise left, rise right. Okay. We know our x-intercepts are negative 1 and 1. Here's the negative 1, 0, and 1, 0. And again, I don't have to label these points because I have them labeled in my work, because I know I don't want to kind of conject the graph here. The y-intercept is 0, 1, so I know this is the y-intercept. Okay. And it's telling me that's going to rise left, rise right. So it looks like I'm going to rise left, rise right. It should go like this. And it says, we've got to draw that real quick. One more time. At these zeros, we talked about a multiplicity of 2. So at these zeros, even multiplicity, graph touches each 0 and then turns around. So if the graph is touching this, it doesn't go through it, it turns around. So it turns around, so it should come back this way. Turns around, and it comes back up to this y-intercept. And same thing with this 0, it says it touches and turns around, so if it turns around, it should come back up here. And that's the sketch of my graph. Okay? does exactly what it said it would do. It says I have rise left, rise right. It has these zeros. It touches each zero and turn around because it has a multiplicity of 2. My y-intercept is there. I told myself it should have y-axis symmetry. Here's the y-axis. Is it symmetrical across the y-axis? Yes. And max turning point told me I should have 3 turning points. Here's 1, 2, 3. So there's a good sketch of my graph for this polynomial function. Okay. I think I might not have enough time to do the next example before the end of the video. So let me go ahead and stop the video, and we'll go ahead and do this next part, next example in the next part.